Hello, everyone. In my previous lecture, I talked about vector fields. Vector fields are just functions which assign to each point a vector. So in 2 dimensions, every point in the plane is associated with a two-dimensional vector. In three-dimensional space, every point in space is associated with a three-dimensional vector. And we can describe vector fields in terms of component functions. So if in the case of a two-dimensional vector field, one point goes in, the vector field comes out, and the vector field is determined by two coordinate functions, p and q. P and q are both functions of two variables in this case, and the vector field is a function of two variables. However, we suppress the notation f of xy, p of xy, and q of xy in favor of a simpler notation, f equals pq. And we have something similar for three-dimensional vectors. In this lecture, I'll start by talking about line integrals, which is something that's totally disconnected from the theory of vector fields. However, at the end, we'll get to the connection and study work integrals, which are line integrals incorporating vector fields. So let's take a look first at the idea behind line integrals. Time and again, I've told you that an integral is just a sum. And in Calc 1, you usually run these sums over line segments. And in Calc 3, we've been dealing with integrals over regions in the plane and solids in space. Now we're going to take a look at a different type of an integral, which is an integral along a space curve. So imagine having some space curve in the plane, and we want to integrate a function over this curve. So just kind of to give you a quick example, let's say we start with a surface defined by the equation z equals f of xy. For every point on this curve, we can associate the value of this function. And maybe our question is to calculate the area of this curtain that's determined by taking the points on the curve, looking at where they map to on the surface, and then we want to get the area of this kind of curtain-like object. And we'll see that the area can be given by an integral over the curve, over the space curve, integrated against the function. This is giving us the height. And then we have ds, which is the arc length parameter we studied earlier in the semester. Okay, so as you'll recall, the arc length parameter is something we define to talk about a differential distance along the curve. So at every point on a space curve, we take this infinitesimal cut and we consider, an infinitesimal length along the curve given by ds. If you blow up this picture, ds looks like the square root of dx squared plus dy squared. Thinking about taking differential cuts this way and this way. Okay, so zooming in on this picture, you'll remember that the picture you get looks like that. Okay, we did this before. dx, dy, and then ds. Okay, now a typical space curve is given by a parameterization. We have the space curve C is defined by some parametric function, some position function, where x and y here are functions of a time variable t. And given this position vector, taking the derivative, we get the velocity like this. and then one can define ds as the length of the velocity vector, or rather the speed, times dt. So, and just to remind you, the speed is telling you how fast a particle is moving along the curve. And if you multiply this by an infinitesimal amount of time, then the product is an infinitesimal amount of distance traveled along the curve. So this should all be familiar to you from what we did before. Okay, so this is the parameter ds, which occurs in a line integral like this up above. We also have the function we're going to try to integrate, f of xy. And then this integral sign, all this is saying is that we're going to do a sum or an integral over all the points on the space curve. Now notice that if we take f of xy, the height of the function, so this is an infinitesimal piece of the space curve. Up here we have the part of the surface that sits above this infinitesimal piece. And we can think of this all as a rectangle because an infinitesimal piece represents sort of a point. So we get a perfect rectangle. The contribution to the area, the infinitesimal area over the curve and underneath the surface, would be the area of this rectangle, which is given by the height of the function times the width, ds. So f of xy ds, this is our infinitesimal contribution to area. And summing over the entire space curve, we get this formula for the area. We get this formula here. Now, to compute an integral like this, we simply make use of our parameterization. So part of the reason we studied these kinds of curves earlier in the semester is so that we'd be able to use these parameterizations to evaluate these types of integrals. And if we want to evaluate an integral over the curve C, f of xy ds, well, we can replace everything. Thinking of this as an integral with respect to the time variable, we can put everything into an expression related to time. So x and t, these are both functions of the time variable t. In general, this arc length parameter, we write it as the speed times dt. Okay, it's a sort of complicated, ugly looking expression, but this expression here is really just the speed. It's the length of the velocity vector. And then in terms of t, we're just left with a simple integral from a to b. Okay, so all of this assumes that we're integrating over some curve where when time t equals a, we're at this initial point, and at time t equals b, we're at the terminal point.
This is a reminder.
Okay, so now once we have an integral in this form, this is just an ordinary integral in the sense of Calc 1. You can integrate it by hand, or you can grab a computer, plug it into the computer. This type of an integral is just a standard integral. And so we've reduced this abstract kind of integral to something that can be computed. And this integral represents this area, the area of this green curtain. Okay, line integrals are used in lots of different ways, however, not just for computing areas. As we'll see, they show up in terms of calculating the work done by a vector field. This has applications in physics. Okay, so here's an example of how you evaluate typical line integral. It's all pretty straightforward. So the question is asking for you to evaluate a line integral over a curve C. Here we have the integrand ds, and C is a curve which is the upper half of this unit circle. So to do this integral, we just follow this method here. First, it's good to make a sketch of the curve. So we're going to sketch this curve, and we can parameterize a circle with a single time variable t using polar coordinates. So we'll take x equal cosine t, y equals sine t, and we'll let t go from 0 to pi, and this will trace over the curve once, starting at the point 1, going counterclockwise to the point -1. Here's our position vector. This is our velocity. Here we calculate the speed. In this case, the speed is uniformly equal to 1. And because of that, the arc length parameter ds is the same thing as dt. Okay, so substituting all of this into our abstract integral here, we can replace x and y by cosine and sine respectively. The limits of integration are 0 to pi, corresponding to our range of t. And then ds has become dt. And now this integral, you can just evaluate it by hand. We get this answer. Okay, so line integrals, really to evaluate them, the main thing is just to parameterize the curve. Once you have the parameterization, you can convert a general line integral into an integral which can be evaluated by a computer. Now, there are other variants on this idea of a line integral, and I'll just talk about that a little bit on this slide. So if we start with a space curve, now this is all the two dimensions, but if we start with a space curve in 2D, something like this, and we have a position vector just, which parameterizes the curve, well, we can always compute the velocity, and then we can using this velocity, we have dx is x prime dt, dy is y prime dt, ds is the speed times dt, which looks like this in terms of the derivatives of x and y. We will always want to have a parameterization with x and y as functions of t, and t ranging through some collection of numbers, an interval. The initial point A is sort of the starting point of the curve. The terminal point t equals b corresponds to the terminal point capital B of the curve. And then now we've parameterized the curve so we can do any sort of integral that we want over the curve. And the types of integrals that'll show up take 3 different forms. So we have these line integrals of the type that I just showed you, where we're integrating some function against the arc length parameter. And so converting this to an ordinary integral, this takes this form. Okay, we've already kind of seen this. The main thing that's happening here is that ds is being replaced by the speed times dt, and then this abstract integral is being replaced by some concrete integral from time t equals a to t equals b. And these other types of integrals, and we'll see these as we go along, Sometimes you want to integrate a function against dx. However, you want to the points that you're summing over to be along a space curve. Okay, so we want to take this curve, but then at each point on the curve, we're going to evaluate this sort of an expression. And I'll show you how such things show up. But in this case, converting to an integral over t, we again have the integral from a to b. This is the range of t values. We convert the functions x and y to their definitions in terms of t, and then dx is replaced by x prime dt. So here's an example which illustrates this. Here we want to do an integral over some space curve y squared dx plus x dy. And we'll look at two different possibilities. C, in the first case, C is a line segment from the point -5, -3 to the point 0, 2. And then in the second case, C is the arc of a parabola, this parabola, which goes over the same 2 points. So it connects, so we have two different curves connecting the same pair of points. And we want to compute this integral here in two different ways. So first along this curve, and second along this curve. So to do either integral, you need to, really the thing is you just need to get a parameterization. So for the first curve, C1, which is a straight line, we can, looking at the slope, we see the slope is 1. We put this curve, describe the curve using slope-intercept form, and we see that this curve follows the line y equals x plus 2. And whenever you have a curve which is defined by y equals some function of x, you can always take a parameterization where x, you set that equal to the time variable t, and then from there you work out what the corresponding y is. That's always one method available to you for parameterizing a curve, as long as it's part of a function of x. And so we can use this parameterization will take us over this curve C1, and we'll take C from -5 to 0. So using this parameterization here, we can calculate dx dt, or x prime, which is equal to 1. We can calculate the derivative with respect to y. This is also 1. So in these cases, dx is equal to dt, dy is equal to dt. And so we know dx equals dt, dy equals dt, and we can substitute into here and here. So these two differentials just each equal dt. For y and x, we just substitute using our parameterization. So the original line integral in this case becomes y squared. This is dx, and then this is x times dy. And it's just some polynomial being integrated from -5 to 0. You calculate it, and you get the answer is -5/6. Okay, now let's look at the integral here, but instead of integrating along the line, we're going to integrate along this green parabola. Okay, we want to integrate the same thing, but the points that we're summing over, the points on this curve, those are different. So we should expect a different answer. To integrate the parabola, in this case, we have x is given as a function of y. So one way to get a parameterization is just to set y equal to this time variable t, and then set x. Then we compute x using this equation, and we let t range from -3 to 2. That's because the y coordinate here goes from -3 up to 2 for this green parabola. Okay, so now we have our parameterization of x and y. We have our range of t variables. We should calculate dx and dy. In terms of t, we have these two expressions. And now our original line integral was this thing. Now we just substitute sort of one piece at a time. So the limits of integration are this, which come from this range of t values. We have y squared. Y squared is, in this case, t squared. Dx is this. So here's dx. This thing here is x by our parameterization. And then dy, in this case, is the same thing as dt. And if you pull all the copies of dt to the outside, the rest is just some polynomial. And we integrate that from -3 to 2. And we get 245 over 6. Okay, so that's how you integrate. As you can see, we got different answers, and that's because we're summing over different points. However, there are some, in this part of the semester, we'll learn there are some important examples in which the integral you get doesn't depend on the curve. It only depends on the starting and the end point. This is not an example of that, but we will see examples of that, and we'll sort of characterize when such things arise. Okay, just a few words about 3 dimensions. Everything that I've said, all these examples, and all of the information I've just told you has its analog for 3 dimensions. So doing line integrals in space, a typical line integral might have this kind of a look where you have a function of 3 variables. ds is, again, still the arc length parameter along some space curve, and we want to integrate along the points of a curve. Now, geometrically, it's hard to visualize what are we computing here. It's the area of some strange figure in 4-dimensional space, perhaps. But there are lots of reasons to want to compute such integrals, especially things that involve electric fields, magnetic fields, and like other issues of things that come out in space. If you're trying to do, track the motion of a rocket or something and taking into effect gravity, such line integrals come up in that form. To convert an integral like this, it just comes down to finding a parameterization of the curve. So parameterizing the curve from A to B, and then converting all the terms, converting everything involved into the time parameter t. So this piece here is the speed times dt. This gives us ds. We replace x, y, and z by their definitions in terms of t, and then this abstract integral over the curve c becomes a concrete integral over a line segment from A to B. As we go along, we'll also meet integrals of this form. And the way you deal with them, it's kind of similar to what we did in 2 dimensions. So all the theory just kind of works the same way. So let's just do a couple of examples of this. In this first example, the problem asks to calculate this line integral over a curve, and the parameterization of the curve is given. So we have everything given here. To set up the integral into something that can be evaluated, well, we already know what x, y, and z look like in terms of the time variable t. The only other thing we need once we have the parameterization is we'll need to know what, we need to work out, in this case, the speed of the particle. So let's write r is equal to 2 sine t, and minus 2 cosine t. This curve, by the way, is a helix. Taking a derivative, we get r prime is 2 cosine t, 1, and 2 sine t. The speed, in this case, the length of the velocity vector, is the square root of 4 cosine squared t plus 1 plus 4 sine squared t. And cosine squared plus sine squared is 1, so this simplifies to square root of 5. In this case, the speed is invariant of the time. It's just a constant. And so we have ds is square root of 5 times dt. Now we have everything we need to set up this integral. Our limits of integration will run from t equals 0 up to pi. And now we just substitute. X is 2 sine t, y is t, and z is minus 2 cosine t. Okay, and so that accounts for these 3 factors in the integrand. ds we worked out was square root of 5 times dt. Okay, and now you grab the old computer and compute the final answer. Okay, so we've gotten from an abstract line integral like this to a form which can be calculated, and that's sort of the goal. Okay, let's look at this example. By comparison, we don't have to work quite as hard if the differential we're integrating against, in this case, is dz. Before it was ds. So to get ds, I kind of went through this work. In this case, for dz, All I need to do is take this expression for z and calculate dz is equal to 2 sine t dt, just by taking a derivative of minus 2 cosine t. And at this point now, we already have enough to write this kind of a line integral. We can write the integral from t equals 0 to pi. Now again, we're going to go through and substitute for x, y, and z. We're going to substitute the definition. So we have 2 sine t for x, y is equal to t, z is minus 2 cosine t, and dz is 2 sine t dt. And that's basically it, apart from just doing the final integral calculation, which I'll leave to you. Grab your computer, grab a cup of coffee, whatever method you want to use, and then you evaluate that integral. Okay, if you guys have any questions about any of this, please just send me an email and I'll be happy to answer. Okay, so the last part of my lecture, what I want to do is kind of look at the connection between line integrals and vector fields. And these things are connected because of a very important process, which is called the work integral, which comes out of physics. The idea of work is basically force times distance. It's a measure of energy, and it's the energy which is required to to move something under some force and for some distance. Say you're pushing a refrigerator across the room, you have to apply a certain amount of force, and you'll have to apply more energy overall if you have to push the fridge a longer distance. So work is is a measure of energy, and it's calculated as force times distance. Now this is all fine. It's easy to calculate work if the force is constant and the distance that you're traveling, it's kind of constant, or if you can calculate the distance easily. But suppose that you have, a particle moving through some force field. So you have some particle which is under some force. Maybe this is like an electron moving through some electric field. And you're trying to get the electron from point A to point B along some specific space curve. And so the vector field is exerting a force on the particle at every point. So over here, there's a force. At some other point, there's some other force. Here, there's a force, and so on. And you're trying to move along. Maybe the force is assisting you to move the particle along. Maybe it's maybe you have to push against the force. Maybe it's not helping you. But then how can we measure the total amount of work along a space curve here where the force is a variable? And the distance we're talking about, it's not the distance given by the straight line, but we're going to be sort of calculating the distance along the curve. The answer to this is that if we just slice and dice the curve and we take an infinitesimal piece of the curve, and just look at what's happening with one instant of time where the particle just moved 1 point along this curve. So in this case, at every instant of time, the distance traveled along the curve is ds, and we can use that for distance. Okay, and then the question is how much force is involved? Well, the force vector points along some direction. But the part that's helping us to move along the curve is the amount of force that's directed in the direction of motion of the curve. And as you'll recall, like for a space curve, the unit tangent vector is tells you the direction of motion of any particle. So remember, when you take the velocity vector, the velocity has incorporated into it both speed and direction. The direction of the velocity is the unit tangent vector, and the speed is, well, it's the speed. It's the magnitude of the velocity. Now, what we want to do is take this force vector and look at how much of it is being applied in the direction of motion. And for that, we do a vector projection. We take F, we project F into the direction of the unit tangent vector. And that projection, the amount of that projection is F dotted with T. So at the end of the day, we wind up with this formula. F dotted with T, this is the projection of the force along the direction of the curve. We multiply this amount of force times this infinitesimal distance. So we have force times infinitesimal distance, and the product is then going to be the infinitesimal amount of work. So this expression here represents the infinitesimal amount of work that's involved in moving the point along the curve just one point, one distance ds. When you integrate that and you sum over all the points of the curve, that gives you the overall work. And this is where the work integral comes from. The work can be computed by this integral, the F dotted with T ds, and calculating work is very important in terms of like physics and various science applications. Okay, so now the last the last thing I sort of want to get to is that this way of calculating work is not very convenient. You can try to calculate the work just using this formula, but it's not very convenient. So I want to show you how the work can be brought into a form which is a lot more easy to calculate. So there's actually 3 expressions for the work, and you'll probably come across all of them. This is, by the way, all taking place just in the 2-dimensional setting, but analogs of this hold in 3 dimensions. So I've talked about this first formula for work. It's a line integral of the projected force times the infinitesimal distance. And we have 2 other ways to express the work. This last method of computing the work is actually the simplest method. Okay, now P and Q here, these are the components of the force vector. So we have our vector field F has 2 component functions, P and Q. And these, both these functions are functions of 2 variables. Okay, and those show up in this last case. Okay, so how do we get these expressions? Well, first off, okay, so and this isn't going to be particularly rigorous, but it'll capture the ideas. So how do we get the tangent vector in the first place? Well, you take the velocity divided by the speed, or to put it a different way, it's r prime divided by the length of r prime. Okay, so the velocity has within it the direction of the unit tangent vector, and then we're just taking this by taking the velocity and normalizing it to be a unit vector, you get this unit tangent vector. Okay, and on the other hand, so we've already seen before that ds is equal to the speed times dt. So at least formally, if we have a t times ds, the unit tangent vector times ds, this is, well, it's r prime over the length of r prime times the length of r prime times dt, or r prime dt. And r prime, this is the derivative of the position with respect to time t. We multiply that by dt, then we get dr. Okay, and so at least formally t times ds, this expression in work can be replaced simply by dr. The differential corresponding to position. Okay, so this middle form, this is probably the form that you'll see a lot, like in physics textbooks or even in the math book. When you see this, you should think work. It's equivalent to this definition, and it can be calculated this way. So how do we get from this middle expression for work to this final expression? Here we'll just kind of formally look at this. Well, we have the integral over c, f dotted with dr. Well, r is the vector function xy. It's the position vector. Dr is going to be the vector dx dy. So an infinitesimal change in position is reflected by an infinitesimal change in x and an infinitesimal change in y. Okay, so going back to our integral, if we just put everything in terms of components, our force vector, our vector field has components p and q. And we're going to take the dot product with dr, which is dx dy. And then just computing out the dot product, it's a sum of two products. We have p times dx plus q times dy. And so that's what gives us this last expression for the work. Okay, now I know I've thrown a lot at you today, a lot of different ideas. So I'd encourage you to, work through these things, maybe watch the video with your friends, um, and just work through some of these examples. Let's do a concrete example or two. Let's see. So yeah, let's take a look at this example, and it'll just show you how to go from a word problem like this to setting up the corresponding integral. Okay, so here the problem says evaluate the work for a particle traveling along a curve y equals x squared between -1, 1 and 2, 4, subject to this force field. Okay, so to set up the integral for work, let's first, I think it's useful to make a picture. We have this parabola y equals x squared. Okay, let me try that again. That wasn't a very good parabola. Okay, well, maybe that's okay. We're starting at some point -1, and going to some final point 2, 4. And this is along the parabola y equals x squared. Okay, and our method or direction is this direction. Okay, now let's parameterize the curve. So because the y equals x squared everywhere here, I can use a parameterization where I take x equal to t, y is equal to t squared. This will give me dx equals dt, just taking some derivatives. dy is equal to 2t dt. Okay, the formula for work, by the way, that I'm going to be using is this last one, where we have the integral p dx plus q dy. Okay, and so we have now our parameterization. Our value, or t value rather, goes from -1 up to 2 with this parameterization. And what else do we know? Our functions p is equal to the function xy, and q is the function x plus y. So this is actually all you need. This is all you need to set everything up. So starting with this definition of work, we can write this first as the integral over c xy dx plus x plus y dy. And now I just want to convert everything to the time variable t. So we get the integral from t equals -1 up to 2. Okay, now we have to substitute for x, y, and dx. Here's x, y, dx. So we get t times t squared, dx is dt. Here we're going to substitute x plus y times dy. So x plus y is t plus t squared. dy is 2t dt. Okay, and let's move these two copies of dt to the outside. We have -1 to 2, t squared plus, well, let's see. Let me try that again. So we have our t cubed here. Here we're going to have 2t cubed, so that'll be 3t cubed altogether, plus 2t squared dt. And I wrote the answer here. If assuming I did everything correctly, that should work out to 69 over 4. And that's all there is. Again, like really the only main problem in all of this is like parameterizing the curve. And once you're there, the rest is pretty straightforward. So it's all about taking setting up a generic integral or abstract integral for work and converting it to something that can be evaluated. In this problem, let's do this last problem. We have the same conditions as before, except we're going to take a different path. This is now the path that this is a straight line path that connects from -1, 1 up to 2, 4. Okay, instead of going along the parabola, we're just going to go along this straight line. How can we parameterize this? Well, we have the slope of the line, rise over run, it's 3/3 or just 1. So we know our line is then y equals x plus y equals x plus 2. Okay, so that's the line that in this case that this curve is traveling over. In our parameterization, in this case, we can take x equals t, y equals t plus 2, dx equals dt, dy equals dt, and t will run between -1 and 2. Okay, from before, the work that we're trying to calculate is this. Let's see, so in this problem, the force field didn't change, so we're still interested in calculating this integral. And so we can convert that to an integral from t equals -1 to 2. So now we have a x times y times dx. Here's x, y, dx. That's t plus 2 dt. Then we have x plus y times dy. So x plus y times dy. In this case, dy is dt. And so if you put everything together, see, in this case, we've got a t squared. This is 2t, 3t, 4t plus 2. And if you do this integral, you get 15. Okay, the answers that we get for the work are different. They're close. 69/4 is what, 15? Well, I don't know what it's close. 17. Okay, maybe it's not that close. And but anyway, it's in the same ballpark more or less. The answers are different, and as we're going to see later, that the reason that they're different is because this force field here is not conservative. So if this were a conservative force field, we would be getting the same answer since we're traveling between the same pair of points. However, it's easy to test using what I showed you the other day. It's easy to see that this force field is not conservative, and that's actually the reason why we get different numbers here. Okay, this last problem, I'm going to leave it to you. Taking everything that you know from this video, I'd like you all to think about how to do this. I'll write the answer myself and post this with this lecture notes. But I'd encourage you to think about this question first without referring to the notes and try to set up the integral and see what you get. So in summary, here's where we are at this point, and this is all the information that I've covered about vector fields, line integrals, and work integrals. The key to doing all of this is just to go back and revisit, the method we had for parameterizing curves in the plane or in space. And I see here is a typo. This should say space curve. And with that, I'll wish you a good day. I hope that my explanations were clear, and please feel free to email me with any questions that you might have. I'll see you soon. Bye.